I have to finish the entirety of one case. It's not even finished. I don't know. You're about to go into med school, you're still watching One Piece. I started already on one season. I watched it. So I'm on Skype. I'm on Skype. I did like copy and paste. I'm on Skype, but I also started. Thank you.
This Friday, so you've had it for 2 class periods at this point. You keep just like pushing that, kicking that down kicking that can down the street. Some expression like that. I also put up the next 2 assignments, and they're currently due next Friday. The idea was sort of that we would master the first 3 or 4 units of this before your mock exam. I was trying to take some of the pressure off of when you did the homework, but still trying to hold you like quasi accountable. If it ain't working, you know, let me know. Clearly not working. That's great. How was your U of H math test? I know. But you didn't come? Oh, I heard I did the calc. You didn't go? You didn't even have to get up. They don't commute if we use that, like matrix multiplication, like A times B is not B times A, it's the same. Huh?
It'll never get back.
They're different.
Are you talking about the protein question? Like why it can be 2 different? Oh, I just literally, isn't there 2 like of those functions? Can you just put one of those?
They decided the other product is water, from what I am overhearing, and Margaret is not an expert at biology. So she's trying to figure this out. First homework assignment, hardest homework assignment, Margaret. I feel like it assumes a lot. Like I actually teach that in this set of notes. They ask about it in that set of notes. Oh, you know, I'm just trying not to miss the middle table. It's a habit.
There's a spectrum to me.
Put all this straight to bin. How's everybody's weekend? Slept, rested, and turned in your math IA? That is flexing on the whole room there. Wow. When did you sleep, Karthika? 12:01?
No, I submitted at like 5:30. I submitted at 6 actually. But it's not. I submitted at 12 hours. That's what you did. Yeah, you did. I know it could be better. You know, like there's a lot of things that I
booster stuff kind of scares me.
It's not good for you.
They make me tired.
I'm sure that you could do a patho unit on like how you break
We did
yourself
something on caffeine.
We did Jefferson.
Caffeine tolerance.
around dinner time. But he did the boondoggle. He got permission to have Conroy look at it. So he and Annika made sure you all have a date with Miss Conroy, like stay in a room.
What's the special circumstance of yesterday?
I have no idea. I just heard about it. They're your friends, not mine. I think that Miss Twist asked for some support, and so the support occurred Saturday when she was here for the TAPS conference, but she hasn't had time to tell her kids. So I think that there will be like one last Hail Mary Wednesday or so.
Like, as in, like, the math isn't math.
The math isn't mathing. I don't know, she looked at me and laughed. It's like, am I gonna grade them all on Monday? I'm like, I suppose not. He submitted, he made every change she asked for.
Yeah.
I figure that's where we need to be.
Microsoft screwed up my.
Microsoft is a flaming piece of and you should all figure out LaTeX. Thanks for coming to my TED Talk.
They deleted a whole paragraph of mine.
No.
Yes.
And like, I was like, how did I, and like, I called back and fixed it like 10 times, but like, it's just one, every time there's something wrong.
And like the online word is even more like, but we couldn't figure out Google Docs, like, he just had a function that's like y is equal to x and 2 pi minus x. I don't know. Didn't know how to do that. Piecewise function in Google, so that's my word. What?
No, I don't know, I'm just saying.
Yeah, so Google Docs, he couldn't figure that out, so we went to Word and never went back,
I
but
think what I did for a couple was I went to Google Drawing or something.
You just wrote it in there by
I like
yourself?
drew it, not drew it, but
Yeah.
like I made text boxes and then I just like, yeah.
clever.
Sorry?
That's clever. Like, I would've gone to the LaTeX equation editor and pasted them in his
That's
PDF,
harder, but yeah.
but I didn't move anyone, and I tried to move her, I remember. We had a thing going. It was a long weekend. Yeah.
The smell is seared into my nose.
It's the only dissection I've ever led with that gross smell.
It hurts.
Yes.
It's stuck in my brain.
She did it today.
It's boring. You just cut it in half.
Oh, yeah,
like
that's
it.
it, yeah.
But if you
That's why
just
I was
cut
willing
in
to lead
half,
it.
and then you're stuck with that smell.
Lead.
Oh.
So when I taught bio honors, we had to do some dissections. I felt comfortable and confident with the kidney because it's not a hard one.
You just cut it in half.
I would never do a freaking rat.
Yeah. You cut it in half and then you have to come over and you
You know,
explain
that
how
guy
the
was
blood
sitting
goes
next to
around
me,
it.
that Asian guy,
And
who I
like
thought
the
it
way
was
to
like,
go.
yeah.
And then it's like,
Aren't there like tetrahedral pyramid things in kidneys?
they don't exist there. They don't, you can't see them. So it's just like 2 shades of brown on your cortex of the medulla and there's nothing else. And it's a sheet. And it's so tiny. It's like this big.
Ours is, well, ours is like this big, I think the second one. It's bad.
Yeah. Okay.
I didn't
That's why it
realize
hurts so
how
bad when
tiny
you get a kidney infection. It's bigger than you expect.
So me and Mona went to the Baylor thing over the weekend.
Yes.
And during lunch, we were sitting with Andre and like 2 undergrads.
Yeah.
That were there. One of them was majoring in business and minoring in biochem. And we met the topic of IB came up, so we were talking about IB. And then one of the other girls was, oh, I did IB, I did not do it right, it's an essay with her. And then we showed her, because we were talking about IB chem, and we showed her some stuff that we were learning, like the sheet they gave us last time, and she was like, I did not start learning this until this year. And she's in her 3rd year of college.
Yeah.
And she was like, it was kind of just like,
It's crazy, guys. Like, it's absolutely crazy.
I have studied using college tests before, and it just makes me feel like shit.
It should make you feel like you're well prepared for the next step because you know you're already doing
Did
it.
they take IB?
the girl did it, but the guy was really good.
I got
The girl did it and she, I think,
And she was like, oh, we know why he brought it with him. He just put it. He was like, oh, can you help me with this? I was like, no, we all have
He
to
just
do
brought
this.
the sheet with him.
We're not asking this undergrad.
Why is Andre having it like so handedly, like in his
You just
pocket?
have it with him. You just like draw your fingers out.
He has his whole textbook all in his hand and all the time. Just like,
He just is ready for anything.
Majoring in business, minoring in bio.
I'd just like to point out that my mother was not a stupid woman. She was like a really, really normal kid growing up going to public school in Southern California. She took algebra in college.
Like base level.
Like that was, like she had seen some algebra in high school and first year of college was college algebra. Like she went into, she never finished college, she got an AA, but she was like into business stuff, so she did like business math. Wasn't her strength, but like she went to school in 1965-ish. In 60 years, the expectation has gone from freshman year algebra to freshman year, she's trying to take like linear, right? Like test out of Cal 1, Cal 2, go straight to linear.
Calculus in that grade.
No, freshman.
No, I mean freshman year of college, like she's,
doing calculus now.
but half of you were trying to test out. So going forward, anyone who's in an HL math is gonna be taking like, I don't know, it's gonna be taking calculus A, B, or BC. So you're gonna be able to test out with your IB scores, test out with your AP scores,
Assuming we get that.
assuming you get them. But like, the goal is very much to be getting college placement in high school. Like they're moving that needle up in math, is that correct?
And everything too. I was
But in
like-
everything, yes, like you guys, the expectations are like 4 years faster. Like we expect you to learn 4 years faster than you expected my parent to learn. And I know that's a long time, but still, it's crazy. Like think of all the things she must have known how to do that we don't know how to do. It's not like she didn't do anything, you know?
I was telling the dude undergrad that I was like, because he was the one that was doing with IB, and I was telling him, I was like, because he was listening to us talking about the chemistry, he was like, this is literally insane. And I was like, he was like, no, sorry, they asked like all of us, they were like, okay, what do you think of IB? Do you like it? You know, I was like, do I like it? No. Is it probably good for preparing for college? I said yes. And he was like, don't worry, like it will. And I was like, thank God, because if I was doing all of this just for it to not even be worth, I would.
Yeah.
But yeah, and then he was like, yeah, like it prepares you for like writing papers and stuff, like the IAs
Right.
class, and then the course material is pretty similar. So like the first year it's kind of like relatively.
You made me feel better about my math IA.
Good.
Because his was way worse.
Way
Yeah,
worse.
he did not
On a
have
scale
much
of
left
bad to
in-
worse.
Yeah.
He did not have much left in his paper. And then Andre showed the girl majoring in business his EE on Taylor Swift, and they just had like a moment, like 20 minutes, just talking. Oh my God, no way, you were Taylor Swift. Can you show? Brings up his laptop, like says, okay, this is Taylor Swift. How her perception of men changes from X album to Y album. And she's like, no way, stop. And then he's like, did you buy Taylor Swift? No way, we're wearing the same shirt. And he's like, no. And I was sitting there like eating my fajita, like okay.
Yeah.
He was a sweet boy, but I was like, okay.
Okay, Tay and Andre. Meeting in Houston. So for many of you, the biochemistry is a bit of a review of stuff you know, but like everything in this glorious class, we make it hard as many times, as many different ways as we can. So we're gonna focus more on amino acids than proteins today, and I think that's something that many of you probably haven't done. So the reason I gave you a data booklet is because I think it's around table 32 or 33, you're gonna have all of the amino acids. So we're gonna use them today. We're gonna talk about amino acids being amphoteric. We're gonna talk about their buffering ability. We're gonna talk about what Zwitter ions are and how they exist as anions, cations, or Zwitter ions in solution. We're gonna talk about why protein structures are so diverse in terms of their primary, secondary, tertiary, and quaternary structures. We're gonna talk about how the 3D shape of a globular protein informs its function. I guess for a fibrous protein as well, it's just much more boring. We're gonna talk about enzymes, but more of that is in the HL. But here we will talk about how enzymes shut down if you change the temperature too high or too low, the pH too high or too low, or if you increase the concentration of metal ions. We'll talk about chromatography and gel electrophoresis techniques for finding what amino acids you've got. As on the homework that some of you were talking about earlier, you're going to figure out how to write the dipeptide or tripeptide you form from the condensation reaction of amino acids. We're going to talk about the solubilities and melting points of amino acids real fast right at the start so I don't forget. Forgot. Friday. We are going to talk about the isoelectric point. So if you did open your data booklet to the amino acid name, you'll see that the column on the far right has a number in it. So we're going to talk about what that number means. It's called the isoelectric point with a PI. We are going to talk about my need to drop pens periodically during class. Talk about graphs of enzyme activity. So we'll talk about inhibitors. We'll talk about different types of inhibitors a little bit. But again, most of that seems to be in the HL portion. And we're going to talk about like doing some math on chromatography. No, I still hate slides. Proteins are the most diverse and abundant class of biopolymers. Why would that be? So they're really big, but they're also made out of the most stuff. So if I think about your DNA is also really long, but it's made out of 4 things, whereas proteins are made out of 20. And so that diversity of structure in the R part of the amino acids is going to allow these to fold up in like novel ways and do some cool stuff, I hope. I did not know that they were 50% of the dry mass of cells, but that's why when you look at a vegetarian and you're like, are you getting enough protein? They're like, I eat food. And there's a fair bit of protein in broccoli. What? It's underestimated. What?
Like dark green vegetables and stuff.
I don't know. Broccoli's got a lot. I'm not a walking. I don't know. I don't know. So generally speaking, an amino acid has a structure wherein we have that central carbon. It's going to be bonded to the R group and to a hydrogen and to a Cu and to an amine. We call it a 2 amino acid because the carboxylic acid defines carbon 1 in our chain. And so the amino group is always on carbon 2. In older literature, they were called alpha amino acids, but I think that will never come up, but your book points it out. Congratulations. Do you know what amino acids look like? Like, I mean, if I had a jar of L-carnitine, and I took a scoop or drop or inhalation of it, like, what is the phase? What is the color? What is the... It's a solid at room temperature. It has a melting point around 200 degrees Celsius, as I recall. What color powder do you think it is, Mohab? Like all good organic materials.
Like beige, white.
White. It is a white crystalline powder. For all intents and purposes, you can picture sugar. It behaves a lot like sugar. What is the dominant interaction between unbonded, like just amino acids? Yeah, so if I had another amino acid here and I am not going to make the bond, I am not going to turn this into a dipeptide, I just have 2 molecules of this, how are these guys going to interact?
Hydrogen?
Yes, I have a hydrogen there, I have a lone pair there. I didn't draw the directionality super well, but there's hydrogen bonding between them. So it's a relatively strong interaction, and that's why I'm going to say I expect it to be a lot like sugar. So no doubt, Mohab's like popping the creatine powder. Right?
I mean, yeah.
It's a colorless, odorless, white crystalline powder. I don't know why everyone giggles.
It's no.
That's funny.
Yeah, Moab seems like the kind of person to do that.
2 of these can come together and they can start making my polymer. What do I call the linkage? I call it a peptide bond. I actually call it an amide bond because, you know, I like this class better than that class. In IB chemistry, I have learned in the last week that a peptide is when you have less than 20. A polypeptide is when you have less than 50, and a protein is when you have more than 50 amino acids in a sequence. For me, I need you to know what a dipeptide and a tripeptide is, 2 amino acids and 3 amino acids. I don't think anyone's going to ask you any questions about the rest of these differences, but it is mandated that peptides are super short, polypeptides are intermediate, and proteins have enough length to start to have that diverse tertiary structure. I have read. There are lots of naturally occurring amino acids. I'm sure we've talked about how D-alanine occurs in the capsid shell of your favorite prokaryote, and it's what penicillin targets when you take that glorious drug to kill your bacterial infection. That, however, cannot be used to make protein. In your data booklet, there are listed the 20 that are proteinogenic. That means the 20 amino acids that are used to make protein in a living organism. Oh, we already said this. All amino acids have an amino group and a carboxyl group attached to the same carbon atom. This is always carbon number dose, hence 2 amino acids. The substituent R may be a hydrocarbon fragment or contain lots of functional groups. So your data booklet, we'll talk about that specifically today. Some amino acids are essential. What does that mean? You must eat them to live. So an essential amino acid is one that your body cannot make. You have to ingest it. So when Karthika goes on her happy diet, she can't just eat beans all the time. Beans do not contain all of the essential acids. She's got to, mix that up with some starches and some vegetables. It's really not very hard, but we do talk about mixing foods together so that you get all of the different essential amino acids. Unsurprisingly, carnitine is a hard one for the veg to get. Now you can buy a bottle of it at Amazon. It's supposed to help with weight loss. Do I know? I try really hard to take a vitamin. I can't quite get myself to do that. So have any of you ever had blood drawn and then to see if your blood is good enough? It's so awkward when you're looking for something. They like poke your ear and then they draw with a little tube from your ear the blood, and then they put this in to see if you have enough protein.
Would they take blood from your ear?
That's what they did. Like that's how they measured iron in your blood. The last time I gave blood was a long time ago because I really dislike it.
So they do it once and they just keep a record of that?
No, every time you go, before they stick you, they do a little tiny stick someplace where it doesn't hurt. They just nick your ear, slurp up some blood, and that's what they tested for iron. They did it on your finger and then a capillary tube? Okay. I feel like all of you didn't give blood the last time you were able to here,
They didn't do that though, you don't have to put it in your ear.
I mean, all the sympathy I have. A funny story on that. The person who babysat me, her punishment growing up was if she was over the weight limit, she had to give blood. That's how her parents tried to get her to control her weight. So, it's a fascinating world we live in where people have really bad ideas. Yes, she is here today, but she doesn't teach this period. She might be in room 201. We're terrible to each other. Oh, so now we're going to talk chemistry, Margaret. Let's go. Board is so clean. You really see every smudge I just made. So this is an amino acid. This side, the acid side, is acidic, and this side, the amino side, is basic. I don't know if I said that good, but I pointed well. What do you think might happen? What do acids do? Neutralize.
They lose protein.
They lose protons, says Quinn. And what do bases do? They accept those protons. And so Quinn suggests that we get an intramolecular reaction wherein the carboxylic acid donates its proton to the amine. Oh no, I thought that's what I was supposed to say right here. Okay, I feel like I'm okay. Because the H over here went over there, and then I 3D'd it, so I didn't have to redraw anything. When I did that last class, I felt intelligent. This time, I'm just copying myself. So this is self-plagiarism, everyone. But it's a good one. Oh my God. Oh, I didn't even look at that. Math IA, turn it in. Do you get your score?
Yeah.
On campus, I think it's helpful.
Better be good.
What number starts to be concerning?
I put 25 as a top. I like they're gonna start like side.
So Jennifer Richardson has always been extremely steadfast in saying that it's not so much the percentage, but what it is. So some of you who cite like everyone and Jesus for everything that you write down, like at some point you get so many citations in there, and citations are plagiarized, right? Like everyone should cite something the same way in the same style. And so when we start getting those bigger numbers in the 20s, we will always go to your paper and see what it is. We will never just make an assumption that you are a bad human that didn't follow the rules.
Because I mean, they like flag, like I saw my history paper once, they flagged during World War III.
Right.
And that was paper.
Right.
It depends if you do like I know for my DE, I had like, when I was studying, my Turnitin score was a 38, so I showed this Richardson, like, you really can't do anything.
And that's what I'm saying. So Ms. Richardson has been extremely helpful in taking people's emphasis off of the number and putting it onto the, if this paragraph is identical to another human's paragraph, it doesn't matter that it's only 5%, this is wrong. But if it's 30% because you're talking about in World War II,
If you're doing a lit one, it's really high too because of the quotations.
yes,
It's
the
not all-
quotations, of course. So,
I had a paper where my only plagiarism was my citations. I'm sure I did not just do those citations.
because we try to assign work that we want you to do, right? And so if you were to get away in this, in your senior year by resubmitting your math IA from your sophomore year, say, you might not be learning all of the things that your teacher intends for you to learn. I don't know. Like you can't use your Chem IA for bio. You can't. Any of you having this problem? Okay. What? Smack him around. I know someone was doing like heart rate, like something similar to what Caroline's doing, but I don't know what Caroline's doing, but like making people do jumping jacks sort of thing and looking at their heart rate, but then.
She's doing music, like the effect of music on
Oh, she's doing Taylor Swift music.
Of course she is.
Okay, I don't have enough energy for this. Back to my Spitterine. How many of you can count to 5 auf Deutsch?
So she puts like a Taylor Swift, she puts headsets on you and plays a Taylor Swift song and then takes your pulse.
What was I supposed to do? Like, you started beating the
Andre does. I mean, you might not.
the one, like, what's it called?
Either it's that or the Starbucks along with that.
It depends which song she plays. I'll probably get here again.
Okay, zwei is how you say two in German. Ein, zwei. Drei, vier, fünf, sechs, sieben, acht, neun. Same. Counting in German. You know, it took me a minute to come up with 3, but we got there. So Zwitterion comes from the word two.
Is that Switcher?
Zwitter. Zwitter. It has 2 charges. So it's when you have, I'm going to erase my numbering because it's not pertinent right now. So you can see loud and proud, just the 2 charges that are present. So we believe when you drop a rando amino acid into water, that the proton on the right, the Ku group, will migrate over to the amino on the left. And so we call this a Zwitterion. We frequently draw them in the neutral, non-Zwitterion kind of state, like in the data booklet, to keep our lives simple. but we believe that this is a more honest reflection of what you see. Maybe I'll look at what your slides look like and see how many of these I can skip. Oh, we're killing it. So, is everyone okay with that? So this would be like the neutral or normal sense of it, perhaps? What do you think would happen if I took it out of a neutral solution and I added like an acidic solution? So what would happen if I added H plus? What would H plus find here to interact with? I'm not going to get a positive on both sides, but I am going to pronate the minus, so. I could get it into the cation form if I were to add an adequate amount of acid. And what do you think would happen if I added hydroxide? It's going to steal that proton that the amine took. It's going to stay the carboxylate. And this would be the anion form. Does this remind you of buffers? So here we took something and we added H plus to it. It kind of stole the H plus and turned it to a weak acid. And we added a base to it. It kind of ate up the base and turned it into a weak base. So this is exactly what we wrote down for buffering. So I like buffers, and I know you do too. And so there are a few things we knew about buffers. Ooh, the pH function is monotonically increasing, everyone. So that's Spearman's rank. It's going to work out just right for you. I'm showing you the volume of base added and the pH. I'll point out some highlights. This would be the equivalence point. At this point, we're taking a weak acid. We're adding a base to it. At the equivalence point, we have equimolar amounts of both of the reactants. And so all of the weak acid is converted into weak base. It's right there, weak base present. You can do that calculation. You may not want to, but you can. You can do the calculation right here before you've added any base. You have a weak acid in solution. If someone told you the Ka, you can tell me the pH. I'll put an only here as well. There's one other point on this curve where you can definitively tell me what the pH is. Oh, at that point of inflection in the middle, in this heart of the buffer zone,
Never got a single one of the questions right.
what is the pH? Saddle point. So he's going from concave down to concave up. This is the second derivative changing sign. First derivative not changing sign. Monotonic increase. What is it? No! Okay, everyone who's looking for a number, stop. It's a letter formula. We're all thinking that, Amarachi, but I'm going to write it down just in case you wanted it really clearly. That's the point where the pH is equal to the pKa. So if this were vinegar, this point would be 4.76.
Of course.
So I know that you really loved this part. I remember it fondly. You might recall that buffers calculations are not in papers 1 and 2. Where would you find a buffer calculation? Oh, paper 3, yay! It's going to be the HL part of the proteins unit. So we will learn how to do this in some other parts, but you do know this answer. It's going poorly. So I was trying to get to this picture right here. So you might recall this is my zwitterion, or what I think of as my neutral amino acid, just hanging out doing its thing. If I add H+ ions, I got to the acidic form. So this side stayed protonated, but the carboxylate took on its hydrogen. If I removed H+ or added OH-, we got to the anion form. And so on this graph, what I'm graphing is pH along my x-axis, and along my y-axis, I'm showing you the concentration of the different species. The reason that we went down memory lane was because we actually know right here and right here at that half equivalence point, when we have equal amounts of an acid and its conjugate base, that the pH is equal to the pKa. So they tell me that that first pKa has a value of about 2. They tell me that that second pKa has a value of about 9. You notice that the Zwitter ion is the dominant form between 2 and 9. 2 plus 9 divided by 2 is 6.5. The average here is going to be around 6.5. 5.5. All fixed. You're going to notice in the data booklet that this number is actually 6, so that's why I wasn't so nervous, because we find that for the most boring examples, this value is not maybe a straight math average, but for the most boring of amino acids, where the R group does nothing with acids and bases, we find that the center of that occurs around 6. So if you have your data booklet open to 33, thank you. I was trying to read upside down on Elizabeth. So why don't you check out alanine 6.0? It has a methyl group. Go down to the bottom and you're going to see butane kind of attached in 2 different ways. For isoleucine and leucine, you just have 4 carbons attached, doing nothing as the R group. What's the PI? 6.3, 6.0? I've shown you the point. I just tried to write down the R group if you have no idea what I'm talking about. I have a methyl group and I have 4 carbon chains, so like butyl chains that are attached, where I show these rando lines. I'm just trying to copy leucine and isoleucine. Those things don't have any acid-base behavior. They're also appearing at 6. How about glycine? Also 6. Also that hydrogen isn't doing any acid-base chemistry. It's bonded directly to a carbon. We can flip the page over. The other amino acids are on the back side. And you're going to notice that valine at the bottom, which is a propyl group, is a straight 6.0. But then we start to get a little bit more variability as we start to make the side chains a little more interesting. All of the alkyl side chains, we're doing great, and we're sitting at a PI, or an isoelectric point, of 6. What do you think would happen if I took this R group and I tried to turn it into aspartic or glutamic acid? You're going to tell me which in a second. So I've taken the R group and I have chosen one that's either aspartic or glutamic acid. So hopefully if you find glutamic acid, you're gonna see that that's the R group that I selected. What is that gonna do to this isoelectric point? What is new about having another Cu there? How many protons could this lose? So we believe that there's gonna be another Ka. So here we can go from the fully basic form to the add 1 proton, to the add 2 protons, even to the add 3 protons. We're gonna have another Ka. That other Ka is also gonna have a value of about 2. So what would the average of 2, 2, and 9 be, Amarachi?
2, 2, and 9. 4, 13, divided by 3, 4 and something.
Okay, so she predicts we'd get it around 4 and something if that's how you did the math. If you look at aspartic acid and glutamic acid, we find it's around 3 and something. Again, it's not a perfect average, but the spirit of adding something else with a low value Ka, like that easy to remove thing, is gonna shift this isoelectronic point over here. We're gonna find that it is like a more acidic thing. What if you look at lysine? It's gonna be at the top of the second page. It's gonna have a bunch of CH2s and an NH2. So I'm adding a basic group. So the Ka should be around 9, so Elizabeth doesn't want to math, but she's going to say 9 and 9 and 2 is about 20. Amarachi's going to tell me if I take 20 and divide it by 3, I get
6 and 6, like almost 7. 6 and 2 thirds.
okay, I get something that's bigger than I used to get, 6 and 2/3, but it's going to be bigger than that. Hopefully it's going to be at 10. So I can't really predict them, but I can predict the orders of them.
What is the isoelectronic point?
So the isoelectronic point is the center of this peak. It's the point at which this Zwitter ion is maxi stable.
And in this calculation, are we just finding that point?
So yes, I'm just considering where that point would be. I'm trying to give you some context about why some of the values are bigger or smaller. So if I add something that has a Cu, the value is going to be small. If I add something that has an amine, the value is going to be big. If I add something that's just alkyl, the value is going to stay here centered around 6. I'm going to try to show you why I might do this in a second, so maybe you'll forgive me for the randomness of this. But we'll see. We're going to have faith for a minute? Okay. Mute. So I believe that some of you have watched enough CSI in your life.
Like crime scene.
Oh,
Yes.
right? I love Criminal Minds.
Okay, Criminal Minds, doesn't matter what you watch. So lysine, found in corn. I'll tell you my story. I thought I wasn't going to, but here we go. Did you guys read Jurassic Park? Thank you for having at least the same reaction as the other guys. Yeah, it was a book before it was a movie. Mind blown. Yeah, so in the 80s, Michael Crichton wrote some books, including Jurassic Park. And one of the things he bred the dinosaurs to do was not be able to make lysine. So lysine was an essential amino acid for them. And as an essential amino acid, that meant that they needed to ingest it. And so at the end of the book, you find the dinosaurs have made it to the mainland of Costa Rica, and they're in the heart of a corn farm, eating as much corn as they can because it's full of lysine. That's how the dinosaurs are gonna get you one day. Okay, but meanwhile, we're watching CSI, and in CSI, sometimes what you might find is that they take a gel. The gel could be like made out of seaweed, agar. You guys say agar in a way that I've never been able to say it.
Agar?
Seaweed juice. It's like really thick jello. And we're gonna put it inside a rectangular tray. And I've actually like put something in there, like a comb, we call it. And I put the comb in there before the jello sets, and so when I pull the comb out, there are these little tiny holes. And so inside those little tiny holes, I use biologist's best friend. This is a pipetter. So you set the volume that you want to pipette. It has a little tip, I don't have any of those. And it will squirt in just a little bit of DNA. Now DNA has a phosphate backbone. And that phosphate backbone takes on a negative charge in water. So DNA naturally holds a minus charge. You can imagine that the histones are positively charged, and that's why we can wind all that stuff around the histones and take chromatin and turn it into chromosomes, another one of them self-assembly things that don't make no sense to me, but you guys are like, yep. And so here we're gonna have some standards. And here we're gonna have Emma, and here we're gonna have Quinn. We're gonna have samples of their DNA. Now, when we sample your DNA, we often cut it up. We cut it up because there are pieces of DNA that are common to us all. And so we can use restriction enzymes to cut it, those pieces that are common to us all. And we can see if there's anything different in between those pieces. But when we're looking at DNA, traditionally we're looking at how long it is. So I have a standard and I have my two suspects, you might call them. Now because DNA is negatively charged, now, is phosphate? That's a shitty question. I don't know how to ask. So I'm imagining phosphate, I'm sorry this is not a good question, but I'm thinking about Amarachi's phosphate buffers. She knew that if she had or your phosphate buffers, right? If you had equal amounts of the monobasic and the dibasic, you were at a pH of around 6 or 7. But if you had more monobasic, it would go down. And if you had straight phosphoric acid, it would go further down. But if you made the pH 10, how would the phosphate look?
Like what it's made of or the pH?
So I'm saying that you in a pH of about 7 had a nice healthy mixture of these two materials. If I took the pH down to 1, I am claiming that I would have this material. And I was asking if I took the pH up to about 11, what material do you think I would have? Would it be protonated or deprotonated if I put it in a really basic sauce? Deprotonated. So I would expect that eventually I can turn this all into phosphate. So for my DNA to take on a minus charge, because of that phosphate backbone, I have to be really careful about what the pH of my system is. And so if you've ever done gel electrophoresis, thanks to the biology or biology honors program at this school, perhaps not during COVID times, but we have this stuff, you might know that you had to bathe this all in a tris buffer.
What?
The other class, some of them did it.
Oh, yeah, just remember him because of the rap battle.
Both bios have done it.
Wait, what did we had to do this?
She's saying that people who might want to do it now.
I didn't either.
You did it?
We did a little coaching.
Okay. Just like doing it for real. Okay, so I put my stuff in a buffer to make sure that my stuff is negatively charged. That was the purpose of the buffer. And I have put a big battery to make sure that the bottom of my thing is negative, the top of my thing is positive, and that's going to take these negative DNAs and make them move. They're going to be attracted to the positive side. Now we have DNAs of different lengths. They're trying to snake through this jello thing. Which ones are going to move the furthest? Farthest? The distance? Short ones. And so in the standard we might find that we have some 100 kilodalton and some 200 kilodalton. What's a dalton?
It's the guy who did the.
Is the guy.
The plum pudding thing?
Yeah, he's the guy who came up with the notion of atoms coming together to make molecules. He's the one who reinvented atoms. But my experience of biologists is that they're terrified of moles, and so they don't call it grams per mole, they call it dalton. It sounds more friendly. It's the same thing as a gram per mole. It's just the molar mass of this stuff. It's big.
I remember Mr. Holmes trying to explain what a mole was. It's very funny.
Or a double. He hates biology. Or he doesn't hate biology. He hates chemistry. And so I put Emma and Quinn twins' DNA through the same machine, and I was able to find that everyone has a band here around 300, but only Quinn has a 200 and Emma has a 100, and so we could say, like, she not the baby daddy. That's funny for a lot of biological reasons. I don't know what we're trying to do, but this is a pretty common way to fingerprint DNA, either to match it to a suspect or to match it to an offspring to try to figure out, are these two things related to each other? Any questions about this? This is not part of our curriculum, but I thought familiar to you because you did a worksheet 2 years ago. Divide by some number, a big number. I don't know, I'd look up like the most averagest of all of the DNA nitrogenous bases, but then I have to show, like I have to throw a ribose, like I would add up all the nucleotides, sides, that's the everybody's tides. Sides is the ribose, tides is the divide by. Hush. Straight up mocking me now. Okay, other preguntas on this that are less embarrassing.
What does the R group have to do with the DNA?
We're coming to that. So this is DNA, and we don't know poop about DNA. DNA is higher level only. I just thought you guys had done this experiment because I have bought this stuff many times in a row. Spent a lot of money on this kit, so I would just like everyone to feel.
I mean, the image looks familiar.
We did a worksheet on it.
Yeah, we did a work.
Okay, I don't know. The picture looks familiar, yeah.
Try.
No, we learned about it.
I feel like we had a little in-class workshop like a
Next
lab.
class.
Let's not give you ready next class.
In place of a tax.
Okay, I'm gonna take that same comb that I used before. Remember the comb just fit into the gel and made the gel like have holes where I could squirt some stuff in. And what I'm gonna squirt in this time is actually related to our syllabus. I know, it's amazing. I'm gonna squirt in some glutamic acid. I'm gonna squirt in some lysine, and I'm gonna squirt in, I'll use better words, glutamic acid, lysine, and tryptophan. It's my favorite. It makes you sleepy, and it's the only one where I know the one letter code for. It's W, so we said tryptophan to each other. There's lots of amino acids in a protein, so they just use one letter to differentiate them all because there are only 20 of them, so it's like a simplification, right? So tryptophan. Whew. Any questions about that? So I have 3 boxes. I have squirted 3 amino acids into them, and I'm going to buffer this at a pH of 5.5. Ooh, let's all look at the glutamic acid together. Glutamic acid, per my data booklet, appears to have a pI of about 3.2. So if glutamic acid is sitting in a buffer that's buffed at 5.5, how do you think glutamic acid might look? Does it feel like it's sitting in its own people? Does it feel like it's sitting in an acidic environment or a basic environment? It feels like it's in a basic environment. And so the glutamic acid in a basic environment is going to look how? Is it going to look like a cation, an anion, or a zwitterion? So if you're basic, what's your charge? And so which way are you going to travel if this is positive and this is negative? And so we're going to come back and we're going to be able to see that this spot has moved up. How about lysine? He's still at the top of the second page. I could have chosen arginine, I just don't know. His PI is 9.7, so what's he feeling?
Okay.
So is he going to be an anion, a cation, or a zwitterion? So he's a cation in an acidic environment because 5.5 is less than 9.2. 9.7. Less than both. And so if you're a cation, which way are you going to move? Now this is 2 units different, and this is 4 units different. How might I see that on my map? My expectation is that the lysine will move farther. And tryptophan, he's sitting there with a PI of 5.9. He's buffed at 5.5. How's he feeling? He's feeling pretty good. Like he should be mostly in his Vitterion state, but if anything, we're in a slightly acidic environment. In a slightly acidic environment, there might be a little bit of cation. And so if this thing were to move, it would move down a scotch. Now, Mo had convinced me that he knew that these were all white crystalline powders. And it's really hard to see that because when you stir them into water, they're all water soluble because they can hydrogen bond. They look like colorless, odorless, like empty solutions. So we have to do something clever to see it. We have to use a locating agent. The same is true of DNA. With DNA, you typically use a methylene blue dye. Again, refer to your worksheet. For this, we often use a chemical known as 9-hydrin. Hydrogen is a lot like lawsone, which Mohab was briefly interested in. Lawsone is the main ingredient in henna. What henna does is it comes, what lawsone does, or what 9-hydrin does, is it comes along and it finds that functionality, and it actually steals the O and the nitrogen from the lawsone or the 9-hydrin, like bonds there. Who did this? Who did this? And it makes this compound brown upon heating. So point here is that you need to use some sort of a locating agent. Probably the 9-hydrin is just a stupid flashcard that Margaret's going to make in about 5 months. Like, it's not meaningful. It's just 9-hydrin. So that's why the R group matters, Quinn. I hope it felt okay. I felt like the gel electrophoresis for DNA was something we'd seen before. I don't know. Are you doing biotechnology for your option in that other class?
You start after this test.
Well, come back and talk to me then. This is biotechnology.
Yeah, I know what that
Another technique that's sometimes used to figure out what amino acids you've got is known as paper chromatography. Did you do this with leaves? Yes. Excellent. That's a beaker. That's some solvent. You can try different ones depending. Oh, shush. That's a watch glass. Hush, everyone. That's a piece of paper.
I wasn't funny to you, hush. I'm sorry.
I just laughed because you laughed.
Oh, shit, what do you mean?
Whatever. On that piece of paper, long and skinny, you draw a line with pencil. It's because graphite's inert. If you use ink, everything will go. That is a pencil line. On that pencil line, you spot, using that same capillary tube that was out, a little bit of your mixture typically. And you allow capillary action to draw the solvent up. It's important you have the lid. If you don't have the lid, you miss a mark. You may have to draw this. Do better than me, apparently.
Wait, so what's the thing on top?
A watch glass just to keep the container closed. You can also use a jar with a lid. Just a lid. Have a lid. The vapor pressure in here has to be constant and known. You want it. The level of the solvent has to be beneath the level of the pencil line. Let's go. We're making a ratio, everyone. Literally what we're doing right now. So what's going to happen is that the solvent, so we're going to put the paper in there, we're going to close the lid, and we're going to find that capillary action, that's adhesion, talk to Elizabeth, is going to pull the solvent up. But as the solvent goes up, the stuff, solutes if you like, have a choice. The solutes have to decide about their relative affinity for the paper, so that would be the cellulose in the paper, and the solvent. So my solvent's going to be acetone. Y'all call it propanone because, you know, cool. What is a striking difference between propanone and water? Okay, it's a ketone. Is it oil? Acetone. You've touched it.
Oh, it's acetone.
I don't care about the double bonds, but yes, it has one. How does it feel when you put acetone on your fingernails?
Oh, the temperature that it evaporates.
It evaporates really cold. It feels cold on your fingernails. Some of you have had your fingers done. More of you than you're willing to admit have had your fingers done. Come on. It's cold. It's cold because it has a pretty high volatility or a pretty low boiling point. That's because the intermolecular forces are strong or weak. They're weak. They're weak because this cannot hydrogen bond. So the salient difference I was going for is that this cannot hydrogen bond. Margaret, comma, lover of biology, read the word cellulose, said, yeah, that sounds good, but can't imagine what cellulose looks like in her head. How would I make cellulose?
Take a plant.
Okay, it's another word for the fibrous material in plants. What is it mostly made out of? It's made out of glucose. So it's a polymer of glucose. Instead of being the alpha glucose that I lovingly drew for you last time, it's going to be the beta glucose. I am not going to draw anything you need to write down. 1, 2, 3 is backwards. This is beta glucose. That's what paper's made of. Cellulose. Grind up plants, mix them with water, and then put them on those like screens to make paper.
So because we put chemicals in your banana, you couldn't eat paper, or like could you eat it regular?
We can't eat paper because we don't have cellulase, so goats can eat all the paper they want.
So if you eat paper, is this gonna like come out as paper?
Yes, it's gonna come out as paper. It will clean your innards.
I took that when I was like a kid, my parents can't remember what like. You just take a.
Was it a note that someone was passing you?
No, I was like in my uncle's car and I just like took like
A little pika between friends. Pika or pika? Pika?
Oh, when you like eat something that doesn't have nutritional value, like ice or like people eat rocks. And, like,
Yeah, people eat rocks.
Ice is the most common. It was just curiosity. I think.
Yes, I agree. I think it's healthy and normal for kids to eat paper.
I can say that.
You've legitimately never eaten a piece of paper? I mean, I don't mean like a full 8.5 by 11 sheet. Yeah, like I think it's normal for people to like. Yes. And that's what the Pika thing is. Like it's stuff that isn't food.
Oh, that's a different realm. It's like Play-Doh, but not. They have like it would have like it would melt on your tongue, right? Play-Doh is so chemically like
It's so salty.
Have you?
I was a child.
I don't know what we're talking about anymore. We're talking about weirder things we've eaten. Yes. It's okay. Paper is like just non-nutritive. Okay, so you are an amino acid and you are making a life-determining choice. Your choice is, do I like the cellulose and paper or the acetone more? What would make me like cellulose and paper? Other than, you know, being a kid in my uncle's car.
The hydrogen bomb.
Hydrogen bonding. So I'm guessing that if I went back to my examples of glutamic acid, lysine, and tryptophan, I assume is what I chose, that Quinn is going to tell me that glutamic acid, lysine, and tryptophan actually each have the ability to form a hydrogen bond. So if you look at their structures, each of them has the capability, but tryptophan seems like it has something else going on. Tryptophan doesn't really seem like it's motivated to hydrogen bond just because it's very big and shockingly hydrophobic looking to me. You guys can tell me how it looks to you. I was just trying to choose the same examples. So when I look at tryptophan, I see that big like benzene ring thing. That looks a little bit hydrophobic to me. And so my expectation is going to be that tryptophan is not going to be as stuck to the paper as glutamic acid. Glutamic acid is going to be really good at hydrogen bonding. It has an OH. So my expectation is that the glutamic acid might not move very far, showing me that it's pretty good at hydrogen bonding to the paper. And that tryptophan might move farther because it's pretty good at sticking to the acetone because it's relatively hydrophobic, and that lysine has a longer tail, and so maybe it will be, you know, just a little bit farther along, has a little bit more hydrophobic action going on. No, the solvent is propanone, but the paper is made out of cellulose. So there's actually water trapped in the paper also. So it's usually a measure of hydrogen bonding in paper chromatography.
So the blue thing, it would move farther because it hydrogen bonds to the water part of the paper. So it would easily like.
So it would stick. So it wouldn't move with acetone as well as it would stick to paper.
The acetone it would trap apart because it's not like bonding to it, so it would just like continue going, and then the
Tryptophan
tryptophan would
dissolve pretty well in the acetone because it's pretty nonpolar. So it has more hydrophobic pieces. It's a big ring molecule. There's like a benzene and another ring. It does have an NH on it, but it's most known for just being like a big alkyl thing. I don't know, I chose the same three examples because they're really good over there and not best over here. We're also going to measure how far the solvent actually goes. We call this the solvent front. The solvent front has to be lower than the paper line because we need to be able to measure it. So you have to pull this out before the solvent has eluted past the top of the paper. Elute is the process of this being sucked up the paper. We can measure, because I feel a lot of pressure, the retention factor as being equal to the distance a spot moved divided by the distance that the solvent moved. Two things with the same retention factor are typically the same.
They like threw someone there.
software real quick.
She left.
God bless.
She's over this. They literally never are in class. Like, ever. There's only someone over here, like, walking around.
It's because that class has a bunch of like
the sciatic just can't handle them.
Oh,
She lets
really?
them have really long breaks because she needs a break.
Like, I feel bad.
Like she
They go through
she like kicks them out. She's like, I don't okay, we're done for right now.
Trickle into our classes after they got it.
Yeah.
Remember those three
Yeah.
weeks?
Yeah.
Everything okay?
Everything's great.
Beat up a couple of sophomores.
Correct a couple of kids.
So just like with the gel electrophoresis, I'm frequently looking at the distance things moved. If I can compare it to a standard, I know what it is. If I can't compare it to a standard, I'm kind of SOL. Here I really do use the nihydrin and put it on a hot plate to make it hot to expose where the amino acids landed. These are free questions. They're so straightforward. Like I know there's stuff to remember, but like this is not super hardcore biology. This is not super hardcore chemistry. I will have paper chromatography set up for you in the not too distant future. We didn't talk about it with the other kids last time. We'll talk more about Jurassic Park, I guess.
What did the tryptophan trap
What?
What did the tryptophan trap?
So tryptophan is the one that was the most hydrophobic. And so it's gonna be the most wanting to interact with acetone because it's a nonpolar solvent. And so it's gonna move with the solvent, whereas something that's really attracted to the paper is not gonna move with the solvent. So you're really looking at an equilibrium constant between like loving the paper and loving the solvent.
Because really it's all paper, but that makes sense.
So you can use water as your solvent and you'll find there's a difference between your love of water and your love of water and paper. And that one's harder for my brain to get around because it seems like it's all water. But the reality is that if I have a known and I have an unknown and I compare them, so there's usually like an athlete and sample A and sample B and was he doping is the flavor of the question that we'll get in this unit.
It's
Doping?
like the kind of question you might see with this kind of stuff.
We
It's
take
like they
urine
have
from an
two
athlete,
samples.
we take a known performance enhancing drug and we see if there's evidence of the drug in the urine.
Based on like the.
Based on this. So paper chromatography is like something you may have done in Science Sizzles with Keith Burton if you've been here long enough. Like it's not it's not a very precise technique. The data that you get from it is extremely qualitative. If you were interested in using this for actually finding out what was in a mixture,
No, I can actually read that.
I don't think she remembers me either. She remembers Max.
What?
Yeah. Yeah, 'cause she showed up one day and Max went over to her and she recognized
I
her.
was in the sciences every year.
I love that class. It started my love of science.
I tried words. So we can use chromatography to identify something versus a standard. That's what we're talking about with the urine and this kind of cheap qualitative technique is, have I made any product? But if I wanted to actually separate a mixture or know quantitatively how much product I had made, I would just take the paper and I would replace it with a thin layer film or with what's known as a column. The difference here is that instead of using the cellulose in paper, I'm actually covering the surface of a piece of plastic or glass with silicon dioxide that I have functionalized in some way. It's extremely finely ground up, it's extremely clean and pure, and the same thing happens, just the resolution is much higher. It costs significantly more money. In a column, you actually take a big fatty column, and you fill it with really ground up sand, that's what silica is, and you pour your reaction mixture through. It has like a burette thing at the bottom, and you take the aliquots and you figure out where your stuff is. It's a way of separating a reaction's products into the one you want versus the others. I'm gonna try to find you a picture of that.
So it's just like a separation column filled with sand.
Separation column filled with sand, yes. Yeah, very expensive, and the sand is so fine that it's really easy for it to scratch up your lungs. And so we were putting chloroform through it, so you scratch up your lungs with the sand, and then you breathe in some chloroform, and it's getting all into you. So you may not want to take the majors lab at Rice. It's a little bit ambitious with all the chloroform.
Is the chloroform good or bad?
Chloroform's kind of bad for you. It depends on who you are, how sensitive you are to it. It's the kind of allergy that gets worse over time.
I don't know.
It's like that like this thing
Is
that
that
like
the
in
thing
stereotypical
Yes.
like things they put it on the towel and they get you and they're like, oh.
That's exactly the
And you
one.
like pass out.
Oh, the kidnapping.
Yes, the kidnapping thing.
No, it doesn't work that way. But we
No,
did
I've
dump a
seen-
4-liter of chloroform in the lab one day. That was exciting.
That was firsthand.
Had prior experience.
The vermiculite to clean up, it turned off by itself because it doesn't trust me.
Why does it make you unconscious?
They didn't fix the mess.
If you look at old option papers, questions will be like, describe a chromatography experiment, a paper chromatography experiment. So you need to talk about the glassware you need, and that's why I said that I was gonna try to make that happen for you, because you deserve it. It's not very hard for me to set up. Any day now when you can see this better. So this is a big piece of paper inside a beaker with a lid on it. You can see the different colors of ink were spotted, and the ink is moving up. Different types of ink in the mixture will move at different rates. That's called chromatography, because if things are colored, it's really easy to see that you have separated them. Column chromatography, it'd really be nice if I had a real picture to work on it. In a second, you really just have something that's like a burette, but again, it can be quite big. And you pour your reaction mixture through, you have solvents at the very top, but different things in your reaction mixture will move at different rates down the column so that you can collect and analyze or quantify them. There are also instruments that do this if you don't have cheap grad students. The instruments are full of even more super fun acronyms. That's what a good looking column. So that's what a column looks like. You actually have a little sand at the very top so that when you pour the stuff down, you don't disturb the flatness of your very finely ground silica. So this is true sand, and this is pay silica. You buy it by the bucket, you scoop it in, you run a little chloroform or whatever through it, you put your solvent on, you put your chemical on, and you're gonna add solvent, and your chemical is gonna elute downwards through it. Different things at different times, you can capture the different bands.
Where did they get the sand?
I don't know, I got it from Fisher Scientific. I don't know where they get it. The two instruments that are used to do this in a more high-tech lab are gas chromatography, where we actually rely a little bit on the boiling points of things. We use columns. It's sort of like a small intestine. Use a really, really long column for this. And different things will elute at different times, partially based on their vapor pressures. And this is high-performance liquid chromatography, which is meant to be a direct analog to that, and it's a little bit more like a large intestine. It's a much shorter space that you pass through. So if you go on to do chemistry, you will do both of these. A gas chromatography setup is almost always linked to a mass spectrum. So you take some business, you separate it, and then you throw it in a mass spec to find out what it is. The first gentleman I dated, how's that for, he worked at a lab where they were looking at how you metabolize drugs, and so they were collecting urine and passing it through a GCMS to try to figure out like what your body was breaking drugs into.
So they're just giving people drugs to test.
No, but they did have a vice president of urine collection because it was a small enough company that everyone could be a vice president. Vice president of urine collection. This is one of the time that the organic chemist is gonna go get coffee. Set your column up, go get some coffee, come back in an hour or two, hope the product's making its way down. Organic chemists, they have a lot of time for coffee. Spend a lot of time in the lab, don't get me wrong. But everything takes forever, so you're expected to work 7 days a week, at least 10 hours a day. We'd really like that 80-hour work week. I'm talking about grad school, so no. So E.J. Corey is a famous organic chemist, and he would not hire people of birthing age because women, you know, they like to take time off to have babies sometimes, and he didn't want that in his lab.
You like sign that away. Does the time that you're waiting still count as your pay?
So that was chromatography. I hope that was a little bit fun and different. We talked about RF factor. We talked about polar solvents and non-polar solvents and how that might affect our groups. We talked about RF values. I threw down that we have some different words. How is it? I don't know. I'll fill in this table and put it in the notes. Thin layer. So it's when you just, like, it looks like you take a piece of plastic and you smear on some of that white sand. It's the same stuff that's in the white sand. So it's meant to be a quick and dirty way to see what the column's going to tell you. Because this will take 30 minutes, but this can take hours.
This is silicon dioxide.
Yes. Yes. So, I mean, in my head, all of these are the same. Like, we're trying to separate. They just give you more and more precision, but take more and more time and money. Okay, I feel fine about that. We did that instead. Do you feel fine? Okay, we're going to talk about primary, secondary, tertiary, quaternary next time. I have homework on proteins. It's due a week from this Friday, so like in approximately 2 weeks. So there's really no pressure, but I thought maybe giving it to you and having a long time to work on it would make things feel better. But it might make things feel worse. I don't know. I'd make it feel better, Margaret, I swear. So if you have a little time, feel free to try to start this. If you don't have any time, we just need to know how to do it before mocks.
I really like this unit.
And also,
Bio, it just connects. Because bio and physics would add gel electric for life system. It all makes sense.
You're gonna do great today. I'm sorry. You've done this.
No, that's mine.
It's meant to be the same. Or she did.
That's right.
Yeah, I forgot to hit that button. I forgot my badge today. It's the beginning of my failures. I haven't tried that printer. The man was there working on it Friday.
Your wall.
Do you need to print
Yeah. Say bye, Moheb.
Adios.
Make sure to subscribe, guys.
You're like 10.
Oh my god, is that the birthday boy right there? Is that
Is it your birthday?
Is that